Assalamualaikum warahmatullahi wabarakatuh and a very good day. I'm Ahmad Fitriadhy from School of Ocean Engineering, University Malaysia, Terengganu. Hello everyone, welcome to our MOOC program for the second video of hydrostatic calculation, topic Simpson rule part 2. Continuing from the first video, using similar way, the area under curve for another accelerated three ordinate of y2, y3 and y4 can be derived as A is equal to h over 3 times the sum of y2 plus 4y3 plus y4. Merely, if we further extend the three ordinate of the under curve, there are yn minus 2, yn minus 1 and yn. The equation of area under curve will be A is equal to h over 3 times the sum of yn minus 2 plus 4yn minus 1 plus yn. Dear all students, based on the segmented of each three ordinates commencing from yo till yn, then the complete derivation of the total area under curve using the first Simpson rule is A equal to h over 3 times the sum of yo plus 4y1 plus 2y2 and plus yn. As I have mentioned before, the notation of h is the common interval or equidistantly spaced between two respected ordinates. As we may know that this common interval is obtained through dividing the total length of the curve by the total number of the ordinate. Referring to this slide, the derived equation of the first Simpson rule as written in the previous equation simply through prominent points can be concluded as follows. First, the pattern of the multiplier number is 1 for 1, which is repeated as 1 for 2, 4, 2, 4, and must be ended by the multiplier number 1. And the second, the n number of the ordinate under curve is odd. Dear all students, once we completely understood the first Simpson rule, the next one is to understand the second Simpson rule. This rule assumes that the equation of the curve is of the third order equation. Here, the function of y is equal to ax power 3 and plus bx power 2 plus cx plus d, where a, b, c, and d are constant. According to the figure 6, we see together that the total number of the curve is even. In this case, we could not blindly apply the first Simpson rule to find the area under curve, meaning to say that the first Simpson rule is not appropriate anymore to be applied, especially finding the area under curve. The primary reason is due to the total number of the ordinate of the curve was not odd number, but it was even. Dear all students, as referred to the figure 7, the n number of the ordinate is even. I can say easily here that the n number is 4. When we are facing this situation, meanwhile, we are required to find the area under curve, the second rule of Simpson is the most appropriate to be employed. Dear all students, however, we should be noted here that we are not going to derive the equation for the second rule of Simpson, as well as done to the first rule of Simpson. But to shorten from the deriving equation, I just want to write instantly the equation of the second Simpson rule as written here, that A is equal to 3/8 times to sum of y0 plus 3y1 plus 3y2 and then finally plus yn. Simply, we highlighted the point here that the second rule of Simpson can be applied when it fulfills the criteria as follows. First, the n number of ordinates under curve is even, and second, the pattern of multiplying numbers should be 1, 3, 3, 2, 3, 3, 2, and then must be ended also by 1. Dear all students, coming to the last Simpson rule that we are going to understand here is the third rule of Simpson. Referring to the figure 8, we are required to find the area between two consecutive ordinates y1 and y2 when three consecutive ordinates are known. As referred to the figure 8, the rule states that area between two consecutive ordinates is equal to 5 times by the first ordinate plus 8 times the middle ordinate minus the external ordinate, and then all multiplied by 1/12 as the common interval. In other words, we can say that the third Simpson rule is sometimes called as 5/8 minus 1 rule, where the final derivation of the equation to find the area under curve can be written in equation 16. Here, the area of two consecutive A is equal to h/12 multiplied by the sum of 5y1 plus 8y2 minus y3. Dear all students, referring to our third objective, in this slide we use the Simpson rule into real application in the naval architect field. We see the equation appears here. In the equation, given the length of the boat is 20.36 meters, the respected water line has equidistantly spaced half ordinate commencing from aft to forward as seen in the slide. Here, we are required to find the area of the water plane, longitudinal center of flotation, and the TVC at this draft. In this slide, before we answer the question, we make a simple sketch translating the ordinate number of water line to be form of the half water plane area of the ship. As seen in this figure, the common interval is determined through a total length of the boat divided by total number of equidistantly spaced ordinate, where the value of CI here is 20.36 divided by 10 is equal to 0.2036. Dear all students, it should be noted here that the final calculation of the fully water plane should be multiplied by 2, since we are here only consider the half ordinate of the water line. In addition, one more important point here is the total number of the ordinate is odd, then it should be bear in our mind that the first Simpson rule must be applied to solve the problem. Once we have already the simple sketch, then we put all input data of the half ordinate of the water line completely into table. As presented in table 1, we then insert the ordinate data denoted as number 1, and then Fs is short form factor of Simpson denoted as the number 2. The product 1 here is resulted from the multiplication between number 1 and number 2. We obtain here that the product 1 is equal to 56.71. Furthermore, the Fm or factor of moment is assigned as the number 4. This Fm is taken from half of the boot as the reference point. Finally, we have the product 2 as the multiplication between the product 1 and the factor of moment is equal to 544.609. Dear all students, as referring to table 1, to find the water pen area of the boot is obtained as a WP equal to 2 times 1/3 multiplied by the product 1. We get the water pen area is equal to 76.974 meters square. In addition, the longitudinal position of the center of flotation is found through dividing the product 2 by the product 1, and we got here as 8.904 meters from after perpendicular or FOAP. Finally, the ton per centimeter or TPC is obtained as water pen area divided by 97.56, and we get that the TPC of this boot is equal to 0.7889 ton per centimeter. Dear all students, continuing for the question 2, a ship 26.35 meters long has equidistantly spaced fully ordinate of cross-sectional area, unit meter square here, commencing from up where the data are shown below. The question is, find the displacement of the ship when floating in the salt water and also her longitudinal center of buoyancy or LCB from midship. Dear all students, referring to the question number 2, let's take note here that we are required to find the ship displacement and also the longitudinal center of buoyancy from the midship as the reference. The data provided in this slide is cross-sectional area from up to forward of a ship. Similar to what we have done in the question number 1, to answer this question, firstly we should draw a sketch as shown in figure 11. We hope that this sketch can assist us to have a clearer figure in capturing the proper solution with respect to the equation given. Furthermore, from the figure, we determine the value of CIOH, which is obtained through dividing the length of the ship by the total numbers equidistantly spaced ordinate. Here, the value of common interval or CI is equal to 26.35 divided by 12 is equal to 2.195. We noted here that the n number of the ordinate is even. Then we should apply accordingly the second rule of Simpson, where the complete calculation is presented in the table 1, and please see in the next slide. Dear all students, similar form to what we have seen in the table 1, in this tabulation data, we insert the ordinate of cross-sectional area commencing from the ordinate number 0 to 12, and finally we have 2 products. There are product 1 and product 2, where this product data will be used to find the vol of the ship and also the longitudinal center of buoyancy or LCB. Referring to the table 2, the vol of ship is obtained as volume is equal to 3/8 times 2 h times 2 product 1. Here we get it as 312.709 meter cube. Then the ship displacement in salt water is obtained through multiplication the vol of the ship with the salt water density. And we have here the ship displacement is equal to 320.526 ton. Regarding to the position of longitudinal center of buoyancy, we calculate it as a product 2 divided by the product 1, and we have the value of LCB is equal to 11.764 meter from forward after perpendicular. Keep in our mind that the question given is the value of LCB from midship as the reference point. Therefore, as seen in the slide, we have finally the value of LCB is equal to minus 1.41 meters. The negative signs mean that the position of longitudinal buoyancy located behind the midship. Dear all students, I do hope that this lecturing provides a lot of insight into understanding the Simpson rule estimation into problem solving of the naval architect field. Before we complete this video, let me summarize several conclusions as refer to my explanation regarding to the first learning objective. They are as follows. First, basically the Simpson rule is one of the numerical integration technique that usually used to find hydrostatic properties in the naval architect field. Second, the derivation of the Simpson rule is successfully done, especially for the first Simpson rule. And the third, we have applied the Simpson rule to solve the problem related to the estimation of the ship hydrostatic properties. Thank you very much for watching